Welcome, curious minds. Today we're pulling back the curtain on a protocol that's probably powering some of your favorite internet experiences right now, often, without you even knowing it.
Right.
You're familiar with TCP, the workhorse that ensures your web pages load perfectly byte by byte. But what about its rebellious, speed-obsessed sibling?
We're taking a deep dive into UDP, the User Datagram Protocol. And yeah, while TCP gets most of the glory for its reliability, UDP is really the unsung hero behind a surprising number of applications where speed isn't just a preference, it's critical. This deep dive is really for anyone navigating the complexities of networking, cybersecurity, cloud services, and especially real-time applications.
So our mission today is to move beyond just the basic definitions and really unpack the fundamental, let's say, engineering philosophy behind UDP. We want to show you why its lack of features, and I'm using air quotes there, is actually its greatest superpower in specific scenarios, and reveal its indispensable role in everything from, online gaming to streaming video. We've drawn insights from a whole range of networking concepts and practical questions to guide us.
Yeah, our goal is for you to walk away with those aha moments, understanding not just what UDP is, but why specific internet services make that calculated choice to prioritize raw speed over guaranteed delivery.
Right.
And what sort of ingenious solutions have been built on top of that core decision.
So let's cut right to it then. We know TCP establishes a connection, ensures delivery, reorders packets. It generally offers a robust, reliable stream.
Yeah.
How does UDP fundamentally diverge from that? What's the immediate consequence?
Well, at its core, UDP is designed for speed and simplicity. Unlike TCP, which does that formal handshake and maintains a session.
The three-way handshake, yeah.
Right. UDP is connectionless. Think of it like shouting a message across a crowded room. You just send it, hoping it gets there, without necessarily waiting for an acknowledgement.
Okay.
Each piece of data, called a datagram, is completely independent. There's no session setup, no numbering inherently, no retransmission if something goes missing.
That sounds, well, it sounds almost reckless, prioritizing speed over reliability like that.
Yeah.
So it's truly a fire and forget approach.
It kind of is, yeah.
But that fire and forget is precisely what drives its low latency, right? That's the key.
Exactly. That is UDP's defining characteristic.
Right.
And this design allows for incredibly low overhead. The UDP header itself is tiny, just 8 bytes.
Wow, only 8 bytes compared to TCP's.
Compared to TCP's minimum of 20 bytes, and it can be more with options,
Right.
that minimal header means less data to process, less bandwidth used just to control information, and ultimately faster transmission. For many applications, especially real-time ones, getting the data there quickly, even if some is lost, is far more valuable than perfect but delayed delivery.
Okay, that makes intuitive sense for certain things. If you're willing to sacrifice that guaranteed delivery, where do we see UDP truly shine? What are the common use cases that really lean into this speed over reliability trade-off?
Well, this raises a really important question for system architects. Where is raw speed paramount? And you'd probably be surprised how pervasive UDP actually is. Think of voice over IP, like a video call maybe you're on right now, or live streaming video and audio, think YouTube Live, or maybe Netflix during peak hours.
Right, live events especially.
Exactly. Even online gaming, that fast-paced multiplayer experience, often relies heavily on UDP for the core gameplay data, like player positions.
Yeah, clicks for those real-time scenarios. When I'm in a voice call, I definitely rather have a momentary audio glitch, a little blip, than a perfectly clear sentence that arrives like 5 seconds too late. A little packet loss is often the acceptable cost of immediacy in those applications.
That's absolutely the key trade-off. And another critical, often invisible user is DNS, the domain name system.
Ah, right. The internet's phone book.
Pretty much. Most of your everyday internet queries, like looking up a website's IP address, primarily use UDP on Port 53. Why? Because it's lightning fast, low overhead.
Makes sense for quick lookups.
Yeah. TCP is generally only used there for maybe larger DNS responses or zone transfers between DNS servers themselves.
Okay.
And even a seemingly simple file transfer protocol like TFTP, Trivial File Transfer Protocol, leverages UDP. It prioritizes simplicity for, small configuration file transfers, things like that.
We mentioned TFTP, which you called a lightweight example.
Yeah.
But what about more robust file transfers? Could you realistically build something like a modern file-sharing app on UDP, or is TCP always the go-to there?
That's a great question. For large, critical file transfers, standard, plain UDP inherently lacks the reliability features. TCP provides the error checking, the retransmission ordering.
Right, all the safety nets.
Exactly. However, what's really fascinating is that you absolutely can build reliability on top of UDP, and people do.
How does that work?
Well, protocols like QUIC, which actually underpins much of the modern web now with HTTP3,
Oh, interesting.
or UDT, the UDP-based data transfer protocol, they essentially layer their own error checking, their own flow control and congestion control mechanisms right on top of UDP.
So they reinvent the wheel, but maybe a better wheel.
In a way, yeah. This lets them avoid some of TCP's inherent limitations, like head-of-line blocking. And it allows them to innovate faster because they're not tied to changes in the operating system's kernel TCP stack.
That's a brilliant example of innovation being almost forced, or at least enabled, by UDP's stripped-down design. So if UDP doesn't natively handle reliability, sequencing, or duplication protection,
Yeah.
applications basically have to take on that burden themselves if they need it.
Precisely. And this also extends crucially to congestion control. UDP itself provides no built-in mechanism to slow down if the network gets overloaded.
So it could just keep flooding the network.
It could, yeah. Applications using UDP, like RDP, that's the real-time transport protocol used for media streams, they must implement their own congestion management strategies. RTP, for instance, adds things like timestamps and sequence numbers to the UDP datagrams.
Okay, so it adds some metadata back in.
Right, to help with media synchronization and detect lost packets, allowing the application to decide how to handle them, maybe skip a frame, maybe adjust bitrate, rather than relying on the network stack like TCP does.
What's truly fascinating here is how these missing features, quote unquote, aren't really a bug, but they're almost a feature themselves, pushing complex logic up to the application layer where you might have more context.
That's a great way to put it.
Speaking of nuanced details, does UDP offer any form of data integrity check, like a checksum? And is it always applied?
It does provide a checksum, yes, for basic data integrity. It's a quick check to see if the data likely got corrupted during transit.
Okay.
But here's a crucial detail. In IPv4, that checksum is actually optional.
Optional, so it might not even be checked.
Correct. If an application doesn't implement its own checks and the UDP checksum isn't calculated or verified, data could silently arrive corrupted.
Yikes.
However, and this is important with IPv6, the UDP checksum is mandatory.
Ah, okay. So newer networks enforce it.
Yes. It ensures a baseline level of integrity verification at the transport layer, reducing that risk of silent data corruption in modern networks.
That's a really significant distinction, especially moving towards IPv6. How does UDP's whole connectionless nature impact security? And what does it mean for common network operations, like, say, port scanning or getting through NAT devices?
Right. Well, by default, UDP offers zero inherent security. No encryption, no authentication.
Just sends the data in the clear.
Pretty much. For secure communications over UDP, you absolutely must layer other protocols on top. Things like DTLS, datagram, transport layer security, which is essentially TLS but designed for datagrams.
Okay.
Or IPsec, working at the network layer. Now, regarding network behavior, scanning for open UDP ports to find services is inherently slower and, frankly, less reliable than TCP scanning.
Why is that?
Because a closed UDP port, according to the standard, often just sends no response back. So the scanner has to wait, time out, and infer it's closed or filtered, unlike TCP, which usually sends a clear RST packet.
Gotcha. Makes it harder to map things out.
Definitely. And for NAT network address translation, UDP's connectionless nature means that NAT devices, which map internal IPs to external ones, might forget those UDP mappings quite quickly because there's no active session telling them it's still needed.
Ah, so your connection might just drop unexpectedly.
It can, yeah. This is why techniques like UDP hole punching are so critical. Often facilitated by protocols like SAGRUN in VoIP applications, they help internal clients establish direct UDP connections with external peers, even when both are behind NAT firewalls. It's quite clever.
And we've all heard of DDoS attacks. Can UDP be leveraged in something like a UDP flooding attack?
Oh, absolutely. A UDP flooding attack is a very common type of denial of service or DOS attack.
How does it work?
An attacker essentially bombards a target server with a massive volume of UDP packets. Because UDP is connectionless, the attacker doesn't need to complete any handshake.
So it's easy to send lots of packets quickly.
Exactly. And it's easy to spoof the source IP address, making it harder to trace. The sheer volume overwhelms the target's network resources, its bandwidth, or even the CPU processing the incoming packets, effectively knocking the service offline for legitimate users.
Okay, let's try and connect this to the bigger picture now. How does UDP operate within standard client-server models? And can it support more advanced capabilities like multiplexing or broadcasting?
Sure. In a typical client-server model using UDP, the server simply binds to a specific UDP port number on its IP address and just listens for incoming datagrams.
No connection state to manage.
Correct. Clients just send their datagrams directly to that server IP and port. There's no connection setup needed. It's truly stateless from UDP's perspective, although, of course, applications built on top can simulate sessions using their own application-level identifiers or logic.
Right, the application layer adds state if needed.
Precisely. And yes, UDP fully supports multiplexing. This is fundamental. It means many different applications running on a single machine can all share the same IP address.
How does it know where to send the data?
Using different port numbers. Each application listens on its own unique port. So when a UDP datagram arrives at the machine's IP address, the operating system looks at the destination port number in the UDP header and delivers the data to the correct application that's listening on that port. It's like having different mailboxes at the same street address.
That's a really powerful capability for efficiency on a server. And I think you mentioned there's a key distinction where UDP goes beyond what TCP can do, particularly for reaching multiple recipients at once.
Yes, absolutely. That's where UDP's strength in broadcasting and multicasting comes into play. UDP supports sending a single datagram to all devices on a local network segment. That's broadcast.
Useful for discovery, maybe, like finding printers.
Exactly. Things like network service discovery often use broadcast. Even more powerfully, UDP supports multicast.
What's the difference?
Multicast sends data efficiently to a specific group of devices that have subscribed to receive it, rather than every single device on the network. Think efficient live video streaming to thousands of viewers simultaneously, or real-time stock ticker updates going only to interested clients.
And TCP can't do either of those.
No. TCP, being inherently connection-oriented and point-to-point, does not natively support broadcast or multicast. This makes UDP absolutely indispensable for certain types of network applications that need one-to-many or many-to-many communication efficiently.
Okay, last practical question here. If you're a network admin or developer troubleshooting a network issue and you suspect UDP traffic is involved, what's your go-to toolkit? What tools would you reach for?
Right. For diagnosing UDP traffic, the classics are invaluable. Tools like TCP dump or its graphical counterpart Wireshark are essential for capturing and analyzing the actual packets on the wire.
Seeing the raw data.
Exactly. Nmap can be used to scan for open UDP ports, although, as we mentioned, it can be slow and sometimes tricky. And Netcat, often called INT-C, is fantastic. It's like a Swiss Army knife for TCP UDP. You can use it to quickly send UDP datagrams, listen on a UDP port, test connectivity.
Very handy.
Definitely. And simple filtering is key. With TCP dump, for instance, you can just use a command like TCP dump IIE0 UDP to see only the UDP traffic on your network interface, cutting through the noise.
Okay, great. So let's try and wrap this up for you, the listener. We've really explored how UDP is fundamentally connectionless. It's incredibly lightweight with that tiny 8-byte header, and it prioritizes speed over guaranteed delivery or ordering. It's the silent engine behind things like DNS lookups, smooth VoIP calls, and responsive online gaming.
In stark contrast, you have TCP. It's connection-oriented, has that more substantial 20-byte plus header, and its whole focus is on reliability, order delivery, and robust error handling. It's the backbone for your web browsing. Well, mostly. QUIC is changing that. Secure email, and large, reliable file transfers. It's truly that classic trade-off in network design.
It truly is a fundamental choice. Speed versus reliability, simplicity versus complexity. And understanding why that choice is made for different internet applications, why one is picked over the other, is really key to grasping how the internet functions and evolves.
Yeah.
It's definitely not about one being inherently better than the other, but about selecting the right tool for the specific job at hand.
Exactly. And this maybe raises an important final thought for you to consider. When you think about how many of our modern digital experiences demand that kind of instant gratification, from messaging apps to, say, collaborative online documents, what other underlying technologies might be making similar, often hidden trade-offs, prioritizing speed and efficiency over absolute certainty? And what are the perhaps subtle consequences of those choices that we just accept every day.
That's a great question to ponder. We really hope this deep dive into UDP has given you a whole new appreciation for this often unsung hero of internet protocols and the really ingenious ways it enables our real-time digital world.
Keep exploring, keep asking questions. You'll find the intricate, fascinating designs of technology are really all around you, making the digital world just a little less mysterious.